Hi everyone. Today we are going to be covering section 11.4 from the textbook, which talks about working with Taylor series. So Taylor series tend to be one of the most powerful tools in mathematics that you really get from calculus in any way. I personally use Taylor series in my research all the time. And one of the reasons that they work so well is that we know a lot about polynomials, right? Basically, all of college algebra was spent about all of the information we know about polynomials. And so what kind of in general Taylor series allow us to do is it allows us to take functions, and instead of thinking about them as functions, we can think about them as polynomials, or for example, limits of polynomials. So this is really helpful because it kind of allows us to take something that we might not know a lot about and convert it into something where we have a lot of information about them. So in this section, we're just going to go through maybe like 3 or 4 different possible uses for Taylor series, but I mean there are hundreds if not thousands of uses for these. But we'll go through some really nice examples for how powerful that they can be. So the first type of example that we are going to go through is going to be finding limits. So finding limits. And just as a reference, I'm going to again pull up this list of these Taylor series so that we don't have to calculate them anymore. This section, right, we're not so much interested as in finding these Taylor series as in actually using the Taylor series. Okay, so let's say we would like to find the limit as x goes to 0 of x squared plus 2 cosine of x minus 2 over 3x to the 4th. Now, right, if you evaluate this at 0, we get 0, 2 minus 2, which is 0, over this 3x to the 4th. Now, we could use L'Hopital's rule on this and differentiate a large number of times, actually. But we are instead going to use Taylor series to actually come up with what this limit is going to be equal to. Okay, so really what we're interested in right now is we're interested in this limit. And let me actually write this down a bit farther. Limit as x goes to 0 of x squared, and let's just replace this cosine of x with its Taylor series. So 2, and if we come up here, we can see that cosine of x is 1 minus x squared over 2 factorial. So 1 minus x squared over 2 factorial, which is 2, plus x to the 4th over 4 factorial. 4 times 3 is 24, or 12, 24, minus x to the 6th over 6 factorial, so on and so forth. So we have an infinite number of terms right there. Minus 2 over 3x to the 4th. Okay. Now, we notice on the top here some things cancel, right? We have an x squared here and a minus 2 times x squared over 2. So these two things are going to cancel with each other. Furthermore, right, this 2 we have right here, this 2 times 1 is going to cancel with this minus 2. So on the top, we're actually left with the limit as x goes to 0 of x to the 4th over 12, if I just multiply this 2 through, minus x to the 6th over 6 factorial, so on and so forth, over 3x to the 4th. And this really helps to show why Taylor series are so powerful, right? Because we know if we are evaluating limits as x goes to 0 and the we have this x to the fourth right here, so we can rewrite this slightly, dividing everything by x to the fourth. So this is the limit as x goes to 0 of x to the fourth over x to the fourth is 1, so this is 1 over 36 minus 2x squared over 6 factorial times 3 plus something with an x to the fourth with some things here. And all of these terms over here have at least an x squared in them, right? It's x to the fourth, x to the sixth, so on and so forth. So these are all going to go to 0. And so our limit is just going to be 1 over 36. Right, so when we're dealing with limits, we're at this point fairly decent at taking limits dealing with polynomials. And so Taylor series allows us to change from the limit of something we might need to use L'Hopital's rule in and take derivatives and whatever, into something we can just plug in a Taylor series in order to solve. So another example, slightly more complicated, and one where L'Hopital's rule wouldn't necessarily work. Let's look at the limit. Now, as x goes to infinity of 6 x to the fifth sine of 1 over x minus 6 x to the fourth plus x squared. Okay, and we'd like to know what this limit is going to be, right? Just from this form right here, it's not immediately obvious if this is 0, this is infinity, if it's some number between 0 and infinity. But using Taylor series, we are going to be able to figure out what this limit is going to be. So what we can do is we know that sine of x is going to be equal to this x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. So we can replace things with the limit. Now as x goes to infinity of 6 x to the fifth. And we'll take everything and replace it by a 1 over x. So we have a 1 over x. And then we have a minus. Now instead of x cubed, we have an x to the negative 3 over 3 factorial. So minus 1 over x cubed 3 factorial plus 1 over x to the fifth 5 factorial minus 1 over x to the seventh 7 factorial, so on and so forth. And we still have this minus 6x to the fourth plus x squared. But similar to before, lots of things are going to cancel, right? This 6x to the fifth times 1 over x, well, that's 6x to the fourth. So that's going to cancel with this x to the fourth right here. Similarly, we have this 3 factorial, which is going to be 6. And so we have a x squared from this green part right here and an x squared right here. So those are going to cancel as well. And so we are just left with the limit now as x goes to infinity of 6x to the fifth of 1 plus x to the fifth 5 factorial minus 1 x to the seventh 7 factorial, and continuing off to infinity. Substituting or multiplying this through, right, this is the limit now as x approaches infinity of 6 over 5 factorial, because the x to the fifths will cancel, minus 6 over x squared, 7 factorial, so on and so forth. And all of the terms after this, right, we have an x squared, x to the fourth on the bottom, x to the sixth on the bottom. All of these are going to be 0 with this limit. And so we are just left with 6 over 5 factorial, which if you simplify and do the math is going to be 1 over 20. So in the case where we don't even have fractions, right, in this example here, we can still use Taylor series to come up with limits that are hard to find. So that is just one of the many uses of Taylor series. Okay. So the next thing that we're going to talk about, and this is kind of just a hodgepodge of, sorry, my allergies are acting up. This is kind of a hodgepodge of different techniques that we can do with Taylor series. So the next thing we're going to talk about is integration and differentiation. So integration and differentiation. And as we talked about in section 11.2, right, these are not going to change where my power series converge. So it doesn't change where my power series converges. So what this allows us to do is it actually allows us to greatly expand this table right here. Because I can do things like taking integrals and taking derivatives of these functions right here and get new Taylor series or Maclaurin series for a lot of these. And see, actually, I think all of these are Maclaurin series. They're all centered at a equals 0. So I'd get new Maclaurin series for functions not necessarily on the list. So kind of as a way to show that this is true, let's consider sine of x and cosine of x. This is a nice thing right here. Sine of x and cosine of x. So we know that sine of x is going to be equal to, just coming back up here, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, so on and so forth. This is the Maclaurin series for sine of x. So if we take a derivative of this Maclaurin series, so the derivative of sine of x, well, derivatives are nice because we can just break it up by terms. So the derivative of x is 1, and then minus 3x squared over 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial, right? I just took the exponent, brought it down, subtracted 1, 3x squared. Well, this cancels really nicely. We have 1, 3 over 3 factorial, right? This is 3 over 3 times 2 times 1. So this is the same as 1 over 2 factorial. So this is minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial all the way off to infinity. But if we come up and we look at the Taylor series for cosine of x, we have the Taylor series of cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on and so forth. So we get that the derivative of sine of x is cosine of x just by looking at these Taylor series right here, which is really interesting and something that, it's neat that they do work this way with the differentiation. And right, in general, it's relatively easy to take the derivative of polynomials where the derivative or the integral of some function is necessarily or can be very, very difficult to do. So as an example of this, we are going to use Taylor series in order to approximate an integral. So we are looking at the integral from 0 to 1 of e to the negative x squared dx. And I believe I've mentioned this before, and if I haven't, I guess. But this integral right here, e to the negative x squared, is something that we just can't take the integral of. So there is no normal function. So this means like any integral of this won't involve sines, won't involve cosines, won't involve e, anything like this. We can use computers to approximate what the integral of this is going to be, but we say that it has no closed form, that no matter what we do, we can't actually come up with a formula for what this integral is going to be, right? Integrals are very hard. This is fairly common with not too difficult of functions. But what we can do is we can use Taylor series in order to approximate what this integral is going to be. Right, so if we replace this e to the negative x squared with the Taylor series, right, we have e to the x is the sum, and k equals 0 to infinity of x to the k over k factorial. And so this is really looking at the integral from 0 to 1 of, we're replacing all of our x's with a negative x squared. So we have, for 0, we still have 1 over 1, plus for k equals 1, we have this negative x squared to the first power over 1 factorial plus negative x squared squared 2 factorial plus negative x cubed squared 3 factorial, so on and so forth, dx. Okay. Simplifying this a bit, right, this is 0 to 1. 1 over 1 is 1. And then we have a minus x squared over 1 factorial. I'll leave that there. Plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, x to the 8th over 4 factorial, so on and so forth. So now if we do take an integral of this, rather than taking the integral of something we have no idea how to take the integral of it, we can take the integral of each of these individual pieces. So this simplifies to x, and then we have a minus x cubed over 3 plus x to the 4th over 4 times 2 factorial, minus, sorry, that should be 5th, x to the 5th, 5 factorial, because we add 1 to it, minus x to the 7th over 7 times 3 factorial, so on and so forth, evaluated from 0 to 1. And now we can just do as we did in that first section where we cut off certain values, right? Anytime we plug in 0, we're going to get 0. And so this is going to be approximately 1 minus 1 cubed over 3, which is 1, plus 1 to the 5th over 5 times 2 factorial, minus 1 to the 7th over 7 times 3 factorial, and so on and so forth. So if we cut it off, I believe after a few more terms, so 9 4 factorial minus 1 to the 11th, 7 times 5 factorial, this is going to give us that this area is approximately 0.747, okay, which is interesting. But we can see that because we are very, very good at integrating polynomials at this point in our math career, we can use this, these Taylor series to approximate what the integral of something is going to be, because we can just cut it off at some point and say, okay, well, it's going to be approximately just the first, I don't know, 5 or 6 terms, whatever we have here, 6 terms. Okay. All right, so polynomials, easy to deal with. Functions are hard to deal with. So Taylor series kind of allows us to do this transition between these functions and these polynomials. So now we are going to talk about using Taylor series to evaluate actual series. So using Taylor series to evaluate series. And I talked briefly about this in 11.3 with the sum of the 1 over k factorial being e. But as we talked about in section 10, we really only had 2 different ways we could possibly come up with the value of some series. We either had a geometric series where it was this a over 1 minus r, or we had that it was this telescoping series where a bunch of the terms would disappear. Taylor series instead gives us a whole new wide range of different things that we can actually figure out what the value of a series is. So let's say, for instance, I would like to find the sum from k equals 0 to infinity of negative 1 to the k of 2k plus 1. So this is kind of like the alternating series where it's going to be 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, and so on and so forth, all the way off to infinity. So it's like the alternating harmonic series, but we're just interested in the odd terms. if you remember back from, I think, section 11.2, we talked about this fact. Negative 1 to the k of k is the natural log of 2. So what about if we just have the odd terms? Well, we might expect natural log, maybe natural log of 1.5, something like this. Turns out that's not right, but we'll actually get some pi's, which is really interesting, because if we have all of the numbers, we have natural log, and in this case, we're going to get some pi's. And let me show you how you would go about doing this. So the part of this question that I hid that I will talk about now is using the Taylor series for f of x equals tan inverse of x. Okay, so the Taylor series for tan inverse of x is, if we come up here to our list, is this negative 1 to the k, x to the 2k plus 1 over 2k plus 1. So this seems like a promising thing to use because we have this 2k plus 1 right here. So this is the sum, k equals 0 to infinity, negative 1 to the k, x to the 2k plus 1 over 2k plus 1. Well, these are not quite the same thing at this point because we don't have any x's here. If, however, we say, well, what if x equals 1? Well, then tan inverse of 1 is the sum from k equals 0 to infinity, negative 1 to the k over 2k plus 1. Because 1 to raise to any power is still going to be 1. And we actually know what tan inverse of 1 is. This is going to be pi over 4. So really interesting, right? Series are hard. They end up coming up with things that are not necessarily intuitive, right? Like where this pi over 4 came from. And somehow when we switched from just not including any of the even terms, we went from things with a natural log to things with a pi in them. But this is what the series is. So as k gets larger and larger and larger, and we add up more terms, we're going to get closer and closer to pi over 4. So if you ever wonder, like on Pi Days, so March 14th, right, they'll always say something like, mathematicians have come up with like 10 to the 10 digits of pi, or something like that. And you wonder, well, how do they actually come up with these digits of pi? They use series like this. So they'll just take terms and they'll start adding them together. And eventually these get small enough where they don't affect the higher decimal places, and so you can get lots of values of the decimal place of pi using these series. So yeah, they use definitely different series than this one. This one would not give you decimals of pi very quickly. There are a lot more complicated ones that you could use as well. But mathematicians would use these series in order to calculate decimals of pi. Okay. Let's do another example for finding the value of a series. So let's say we'd like to find k equals 1 to infinity of k over k plus 1 factorial. And I'm giving the hint to use f of x equals e to the x minus 1 over x and f prime of 1. Okay, so if I take the e to the x minus 1 over x, so e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on and so forth, right? So if I subtract 1, that will get rid of this, and dividing by x will get rid of a power of x each time. So e to the x minus 1 over x is going to be 1 plus x over 2 factorial plus x squared over 3 factorial plus x cubed over 4 factorial, so on and so forth. So what ends up happening here is this is going to give us this k plus 1 factorial, right? It's always going to be 1 larger than the power. But I still need this k right here. So in order to do this, I'm going to take the derivative. So dx of e to the x minus 1 over x. The 1 is going to go away, so I'm just left with a 1 over 2 factorial plus a 2x over 3 factorial plus 3x squared over 4 factorial, so on and so forth. And I can see when I take this and plug in 1, so f prime of 1, well, I'm going to get 1 over 2 factorial plus 2 over 3 factorial plus 3 over 4 factorial, which is exactly this series we're interested in. K equals 1 to infinity of k over k plus 1 factorial. But I can figure out what f prime of 1 is by just taking a derivative as normal as I would of this e to the x minus 1 over x. Right, so not in terms of Taylor series, but in terms of our function, f prime of x is going to be equal to the bottom times the derivative of the top. The derivative of e to the x minus 1 is e to the x, so it's x e to the x minus the top times the derivative of the bottom, so minus e to the x minus 1 over x squared. Plugging in 1, I get e to the 1 minus e to the 1 plus 1 over 1 squared, which is going to be 1. So I have two different ways of evaluating this f prime. I have it as this infinite series right here, and I also have it as 1. So the sum of this infinite series is 1 as my final answer. So in this chapter, and in Calculus 2 in general, most times you will be given what f to use and what value you should plug in, unless it's very clear looking at a table what value or what Taylor series to use. So in this case, where it's a bit more complicated, using a non-standard function, you would be given the function and say, okay, compare this series to f prime of 1. Because it's definitely not immediately clear that this is the series you want to look at. Okay. So I now am going to talk about one of my favorite facts in mathematics. I think it's really, really beautiful, and I think it's really neat. So we have that e to the I pi plus 1 equals 0. And we are going to show this using Taylor's series. I'm going to be a bit hand-wavy because we haven't really talked about complex numbers a lot in this class, or any calculus class in general, really. Complex numbers in calculus make things much, much more difficult. They make things a lot more powerful, and you can do a lot more things with them, but they do make things more difficult. So we kind of are going to sweep some details under the rug in this, and you can just take my word that in this case, the Taylor series are going to be equal to the same if we include these complex numbers. Okay, so e to the I plus 1 equals 0. So e to the x is going to be equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial all the way up to infinity. And then we have a couple of additional facts, right? We have cosine of x, I believe, yeah, this is going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, so on and so forth. And also we have sine of x is going to be equal to this x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on and so forth. Okay. So we can see that these cosines and these sines are going to be fairly closely related to each other, right? We have the ones here and then the x's, and then it's almost this. So they almost, if you add them together, they're almost equal to e to the x, but some of these signs are going to be a bit off. So let's think about what happens if I take ei to some number. So ei to some number. Well, plugging in values, this is going to be 1 plus I. And then I have an I squared, which is going to be a -1. So this is IA, and then this is a minus a squared over 2 factorial. I cubed is going to be equal to, right, so we have I squared is -1, I cubed is I to the 4th is 1, I to the 5th is I, and it's going to do this repeating pattern every 4 times. So I cubed is -I, so we have a minus I, a cubed over 3 factorial. The x to the 4th will have 0 i's in them. It's not going to be imaginary anymore. It's just going to be 1. So it's a to the 4th over 4 factorial, so on and so forth. The next term, just to write it out, a to the 5th over 5 factorial. Now if we take this and we combine all of the odd terms and the even terms, right, this is going to be equal to, or sorry, not all the odd and the even terms, but all the terms with I and the terms not with I in them. 1 minus a squared over 2 factorial plus a to the 4th over 4 factorial. And this one would have been minus a to the 6th over 6 factorial, so on and so forth. So these are all the non-imaginary terms, and all of the imaginary terms with I on them. Well, I'm going to have an a. I'm going to have a minus a cubed over 3 factorial. I'm going to have a plus a to the 5th over 5 factorial, and so on and so forth. And we can see from this that something honestly kind of magical happens. It's going to make it so that it's going to be equal to sines and cosines. So e to the ix, if I just use x instead of a, is going to be equal to the cosine of x plus I times the sine of x, right? Because this right here is the cosine of x, and this right here is the sine of x, just matching these two things up. Well, let's plug in some numbers and see what happens. E I to the pi, well, cosine of pi is 1. Sine of pi is 0, so e I to the pi is 1. Oh, sorry, -1, right? Because cosine of x equals, or cosine of pi is -1. So just adding the 1 over, I get this e I to the pi plus 1 equals 0. And this is just absolutely insane, right? That we have this I in here, and we have a pi, and we have an e. So all of these, right? I is imaginary, pi is irrational, e is irrational. But we raise them to some power, and it's going to be equal to -1. And we can see this using these Taylor series right here. And I just think this is really neat. And it really involves a lot of things that we care about a lot in math, right? This e and the pi come up a lot, imaginary numbers come up a lot, and then 1 and 0 are both very important constants in math as well. So this is really interesting. Okay, that was kind of a side note. The last thing we are going to talk about, and this will only take like a minute or two, is just going through taking a series and writing it as a function. So say I have the function k equals 0 to infinity of 1 minus 2x to the k over k factorial. Okay. So this involves a lot of pattern matching. It involves a lot of looking at our table. So if we do pull up our table, and let me just pull up another one so we don't have to scroll all the way back up. we're looking for something that looks a lot like something to the k over k factorial. And if we come down, e to the x right here, e to the x is x to the k over k factorial. Of x to the k over k factorial. And so we can replace all of our x's with 1 minus 2x and get the sum. Oops. The sum. Oh, my pen is dying. I have so little to do left. Let's see if I can get it to work. Nope. I bet it will work with my finger though. No? Okay, well, I don't want to stop and re-record just to spend like maybe writing an extra line, but what we're going to get is we're going to get the sum from k equals 0 to infinity of 1 minus 2x to the k over k factorial is going to be equal to e to the 1 minus 2x. And we can see this just by taking this standard Taylor series from our table and replacing all of the x's with a 1 minus 2x. Furthermore, we know that it's going to converge everywhere because if 1 minus 2x is finite, then certainly x is going to be finite as well. So it converges everywhere, and the sum is equal to e to the 1 minus 2x. Okay, right, so that is the end of the lecture. Thanks for bearing with me as my pen died.